Hello, everybody. I'm Cesar Bertinetti, currently a master's student at the Maya Lab at the University of Constance. And today it's a great pleasure for me to be talking about how the visual sensitivity of crater lake cichlids in Nicaragua is correlated with their photic environment. All right, so what I'm showing here in the left is a beautiful underwater picture of Lake Tanganyika, and in the background you can see the blue color of the water, and this is due to the fact that blue is absorbed less in pure water, in clear water, and hence penetrates deeper. However, as soon as the amount of sediments dissolved in the water increases, this will filter out some of the short wavelengths and hence change the color appearance. So if we think about cichlids that have to deal with these kind of environments, we would expect this to impose a strong selection pressure since they heavily rely on vision for many of their tasks. So cichlid vision, it's highly tunable. However, what I want to focus today in the cone photoreceptors, which are localized here in the retina. This is showing the cichlid eye. And for instance, in humans, we have tricon opsins, we are trichromatic. However, color vision in cichlids is achieved by up to 7 opsin proteins plus a chromophore, but especially the combination of those opsin proteins and the relative abundance of those can highly influence the sensitivity of the eye. And hence, if you would like to maximize the information that you are getting from your light environment, you will try to optimize the relative expression of those opsins. So the reason why we do this in Midas cichlids in Nicaragua is because they are a wonderful system to study adaptation. So here, two source populations from Midas cichlids from the Great Lakes have recently colonized several crater lakes. And of course, all these craters look a bit different and therefore differ in their photic environments. So previously, most of our knowledge has been restricted to two crater lakes, which I'm going to show now the data. So here you can see the light spectra of both Great Lakes. In the y-axis, I'm just showing the amount of light per time at 1 meter depth. And what we can extract from here is the so-called lambda p50, which is giving an estimate of the light distribution, so the wavelength that halves the spectra in two equal parts. And you can also see the spectral bandwidth, which is the called lambda p2575, which gives the 50% of the photons. And if we now compare this to the spectra of the crater lakes, which see that these have been shifted towards short wavelengths, that also the range is wider. And even if we took a deeper insight into the light intensity relative to the surface, we'd see that crater lakes have more light available at 1 and 3 meter depth than the Great Lakes. So we know that somehow there are crater lakes which are clear, white, luminous. On the other side, we have Great Lakes which are turbid, narrow, and dimmer. However, given that we have so many environments, we wanted to know where are those located. So what was done is that the irradiance measurement from all these locations was taken. So basically 7 crater lakes, 2 Great Lakes, 1 river population, and then the light spectra was measured. And here is, I'm showing again in blue, the solid line is showing the crater lake, and in the background as a red shadow, you can see the source populations. And just by a simple eye, you can see that most of them are a bit more shifted towards the short wavelengths. However, what was very interesting for us was the fact that even taking into account all the environments, we see a very strong correlation of the light distribution, the range, and the light intensity, meaning that the more long wave shifted the environment, the more narrow it is, and the less light it's available. So basically, this gave us the power to locate all those environments in our gradient. And the question that has to be addressed now is how is sensitivity or how well is it actually tracking the light conditions across all this environment. So for this, what we did is that 8 adult fish from wild populations were caught, and we analyzed the proportional opsin gene expression via real-time qPCR. And for example, here I'm just showing the long wave sensitive pigment, and you can see that in Great Lakes it's a bit higher and Great Lakes is deeper, and that is what you would expect. We can further do this for the 6 opsins. However, it's also very interesting to try to estimate the sensitivity of those individuals. So basically, by taking into account the proportional expression of the opsin and adjusting this by the absorbance, the sensitivity as a point estimate can be estimated. So here I'm showing you the templates. So this is basically the base in which this builds upon, and then you can take the peaks into consideration. Then this is adjusted by the proportional expression, and adding this up will give you a point estimate of the sensitivity. So these are the values I'm showing you now in the y-axis plotted against the lambda p50, so a proxy for the turbidity of the environment. And what you can see, and this was very interesting for us, was the fact that actually it seems that sensitivity closely tracks the light environment, so that across all environments we see a significant relationship. This was nice, but furthermore, we wanted to ask, given that it was known the colonization history, so basically which crater lakes have been colonized from which Great Lakes, can we somehow explain or at least correlate the change in the sensitivity with the change in the light environment those have experienced? So here we do a similar approach. So we take again into account the absorbance templates of the visual pigments. And now instead of taking a point estimate, we take the whole curve. We again adjust that for the proportional expression. And this gives a so-called sensitivity curve. Then this can be done for all the individuals in a source population, here the Great Lake, and then compared to the crater lake, therefore delivering the shift in spectral sensitivity. If we now do the same approach for the change in the light environment in downwelling irradiance, then shift in spectral irradiance comes, and then how are these two terms correlated to each other was the open question. So here are the results, and this is way better than we expected. So basically, all the values are highly significant. We see that the correlation is pretty strong, and that actually the change in sensitivity, the direction of that change is in the same direction of the photic environment, maybe a bit lower for some of the crater lakes that differ less from the source populations, but nevertheless pretty high. So in conclusion, we can say that Midas cichlids do stay tuned and very well, in my opinion. So we can also say that using both point estimates and spectral curves deliver similar results. We've also tried using sidewelling light or transmission coefficients instead of downwelling. This also gives similar results. And we've even looked into the chromophore usage across environments, which is another mechanism of tuning the system that I don't have time to go into. Okay, so with this being said, I first would like to thank Marena in Nicaragua for giving the permits for catching the fish in the field studies. Then 2 of students in the lab, Femina and Nida, would help me a lot with experiments. And finally, the financial support by an ERC to Axel Meyer and a DFG to Julian Torres Tautau. So thanks for listening, and I will be happy to take questions.